If this is clear, then let us go to the other example that we had taken in the graphical method, which was the case where we had two outputs and a single input, right? So now every sales office has a budget of 2 lakhs, which was the only input, right? But they must achieve whatever sales that they can achieve and generate potential leads. We have described what that potential leads mean. So this was the data. This was the data that we had used for this case where we have two output. Sales is an output, number of leads is an output, and only single input, which is the budget, and actually it is same for all the DMUs. It is same for all the 5 DMUs, all the 5 sales offices. How would we formulate such a problem? First of all, let us understand the O's and I's and the X and Y's, right? How do you interpret the O's and I's? Let us look at this problem as a problem for sales office 1. So what is O11? O11 is the first output for sales office 1. That value is 11 lakhs and 10,000. What is second output for the first sales office? That value is 15, right? O21, right? Similarly, the only input number 1 for sales office 1, that value is, that value is 2 lakhs. Did I add an extra 0 there? No. Okay, so those are the O's and I's. Since we have one input, we are going to need only one input weight. Since there are two outputs, we are going to need two output weights. Right? Which is what is mentioned here. Right? So for every sales office, we are going to have two outputs, O1K and O2K. K represents the DMU, so keep replacing K with 1, 2, 3, 4, 5. You will get the different output values, and these are the weights. X1K, so X11, X12, X13, X14, X15 will be the input weights used by each of the DMUs, and this pair Y1K and Y2K are going to be the output weights used by the DMU K. You change DMU K to be 1, 2, 3, 4, 5. You are going to get the different variables. Y11, Y21 are going to be the weights for DMU1, Y12, Y22 are going to be the weights for DMU2, and so on. So how would we formulate the problem? First of all, how do you define efficiency? Let us take sales office 1. How do you define efficiency? Efficiency is weighted output. What is the weighted output? Here there are two outputs. So Y11 O11 plus Y21 O21. Y21 second output for first DMU divided by weighted input. There is only one input, which is X11 I11. So that is going to be the expression for the efficiency. And how do you translate that to the linear programming problem? You say that I will maximize only the numerator, so this will become the objective function. I will normalize the denominator to 1, that becomes the first constraint. Right? So let us do that. So maximizing the weighted output is going to be the objective function, which matches with whatever we had written here. First constraint is going to be normalizing the input. Normalizing the input is written this way. X11 multiplied by 2 lakhs. 2 lakhs is the budget, which is the only input that is given, and we normalize this to 1. What is this constraint going to do? This constraint is not going to touch the 2 lakh because it's just a value. So this constraint will ensure that we adjust the value of X11 according to this constraint, because this is an equality constraint. What are the other set of constraints? The other set of constraint is using these weights, no DMU should get an efficiency of more than 1. So E1 should be less than or equal to 1, E2 should be less than or equal to 1, E3 should be less than or equal to 1. Let us take the example of E3. What is E3? Using the weights for sales office 1, sales office 3 should not get an efficiency of more than 1. So what is going to be E3? Using the weights of DMU1, so Y11 multiplied by first output for third DMU, Y21 second output first DMU. However, the output value is going to be second output for the third DMU. This is the weighted output divided by weighted input. X11 is going to be the weight assigned by first sales office for input 1. However, the input value I will use, the first input I will use will be for DMU3. Right. And then I move this, so this has to be less than or equal to 1. I will move this to the right hand side and I will write the constraint in a linear way. So this is that constraint. This is this constraint. Are you, do you want to ensure? The only thing that you have to check is whether O13 is really 34 lakhs and O2 is really 12. Just check that quickly. Yeah. So this is 34 lakhs and this is 12. Right. The right hand side doesn't change because input is same for everybody. Input, there is only one input which is budget, and the budget is kept constant 2 lakhs for everybody. Right. So this is the constraint for the third sales office. This will be the constraint for the fourth sales office. 12 lakhs is the sales achieved and 23 are the number of leads generated using the budget of 2 lakhs. And this is going to be the constraint for the sales office 5. This tells you what is the interpretation of this? It tells you that using the weights for sales office 1, sales office 5 shouldn't get an efficiency more than 1. We actually include sales office 1 also, right? Even when we tell you to maximize your efficiency, don't quote a value more than 1 because the efficiency of more than 1 really doesn't make sense, right? Okay. And so we have written the constraints mathematically for all the 5 DMUs. The only thing to be done is to explicitly highlight the decision variables. What are the decision variables? The decision variables are the input weights and output weights. There is only one input weight, X11. There are 2 output weights, Y11 and Y21. Those are the 2 output weights and those have to be greater than or equal to 0, which is a typical requirement of a linear programming problem. Not always true, but definitely true in this case. Okay, one more example, sales office 2, right? Sales office 2, how will you formulate the numerator? Numerator is the weighted output that needs to be maximized. The weights are Y12 and Y22 output weights. So first input, second DMU, first output, second DMU, second output, second DMU. So these are output weights, Y values, output weights. Maximizing the weighted output is the objective function. Make sure that these are the output values for second sales office, 17 lakhs and 10 leads. 17 lakhs and 10 leads, yes. 17 lakhs and 10 leads, 17.5 lakhs and 10 leads. Those are the outputs for second. So 175 and 10, those are the output values. Input value is the budget, which is same for everybody. That has to be normalized to 1. Using the input weights, input weight is X12 because first input, sales office 2. And once again, these constraints are very similar constraints, only the input weight and output weights are going to be different from what we had here, right? Here the sales office 1 was assigning its own weight. Here sales office 2 is assigning its own weight. So the weights are different. The constraint structures are the same. Constraints interpretations are the same. Here the decision variables are the weights to be used by sales office 2. These are the 3 weights, input weight and output weights for sales office 2. And we have seen in the previous formulation that every DMU in fact chooses different values for input weight and output weight because they will use the values that best suits them, right? So very similarly, we have shown formulations for the first two sales offices. Very similarly, you can actually you can formulate the problem for the remaining three sales offices, right? Remaining three sales offices. Right. So once again, very similar approach. Let us go to Excel sheet. Let us go to Excel sheet. This is the Excel sheet. This is the data for the two output scenarios. Two outputs were sales and number of leads. So let us look at. Let us go the other way actually. This was our graphical output. This was our graphical output, if you recall. This was our graphical output, right? So yeah, and obviously whatever we do in Excel LP should match the graphical output, because in fact the graphical output came from DEA. So this was our envelope, efficiency envelope. Efficiency envelope was on the outer side because we are mapping the outputs. So more the better. You want more sales, you want more leads. So the efficiency frontier is going to be drawn outwards, not inwards. Inwards is usually when you minimize the inputs. Here you are maximizing the output, right? So 3, 4, 5, DMU 3, DMU 4 and DMU 5 turned out to be efficient. DMU 1 and DMU 2 turned out to be inefficient in the graphical method, graphical representation. Let us make sure that we can verify this. Let us do this. So I have already identified 3, 4 and 5 to be efficient, right? So let us look at these three first, 3, 4 and 5. So let us look at 3 first. Okay, so these are the, this is the data. Everybody gets the same marketing budget of 2 lakhs, which is the only input. And there are two outputs, sales and number of leads. These are the values for each of the sales offices. Since there is only one input, there is going to be only one input weight. There are two outputs, so there are going to be two output weights. Since this is the third sales office solving the problem, how do you denote the new decision variables? So this is input weight number 1 for the third sales office, output weight number 1 for the third sales office, output weight number 2 for the third sales office, right? So these are your essential values. Okay, now do you want me to write the constraint? Okay, let us do that. No problem. So this is for the third DMU. So these are the output weights. Output weight number 1, output weight number 2 multiplied by the output for the third sales office. That's my objective function. My first constraint is normalization of input. So input weight multiplied by the input which is common to everybody, which is the budget. That is my that was my denominator in the efficiency expression. That has to be normalized to 1. That has to be normalized to 1. So this is your normalizing constraint. Now what are these constraints? These are the constraints just to tell you that using these weights, nobody should get an efficiency more than 1. So this is the numerator. Numerator is the weighted output for the first sales office. This is for the first sales office. And this is the right hand side. This is the right hand side, which is weighted input. Weighted input is input weight multiplied by the budget, which is common to everybody, right? So the right hand side is going to be 1 for everybody here. Right hand side is going to be 1 for everybody here, right? And this constraint tells you that using the weights for sales office 3, sales office 2 should not get an efficiency of 1. This constraint tells you that using the weights for sales office 3, sales office 3 should not get an efficiency of more than 1. If it is efficient, it can report an efficiency of 1, no problem, right? Which is what is happening here, right? It reports an efficiency of 1. Left hand side is same as right hand side. Anyway, the constraint was less than or equal to. So equal to is also acceptable. Similarly, this tells you that using the weight for DMU 3, DMU 4 should not quote an efficiency of more than 1. Using the weight of DMU 3, DMU 5 should not report an efficiency of more than 1. Did we do this nicely? Okay, initialize it to 0 and solve it, and you will get efficiency of 1 for the third sales office. Now notice a few things. Anyway, we have not paid too much attention to the input and output weights because we are right now focusing on who is efficient and who is not efficient. So what weights they end up using actually matters much lesser. But even then, look at something peculiar. So let me highlight that. Sales office 3 decided that it is going to assign a weight of 0 to the second output. What was the second output? Second output was number of leads. Notice that the third sales office has very few leads. Look at sales office 1, 15, sales office 4, 23, sales office 5, 20 leads. In that comparison, sales office 3 looks a little bad on that front. Only 12 leads generated. Has a huge sales generated, but only 12 leads generated. Okay. So very promptly it says, I will de-emphasize number of leads. I don't think they are important. So I will assign a weight of 0, which is okay, which is allowed for a decision variable. Okay, which is allowed for a DMU, right? So we gave DMU the freedom to pick any weight. So why can't they pick a weight of 0, right? There are some DEA formulations where the designer can say that no, you can't assign a weight of 0, you must assign some minimum weight, right? Some minimum weight has to be assigned. If you put that extra constraint, then it will prevent a DMU from assigning a weight of 0 to a particular input or output, right? So this is going back to the cricket analogy. If a bowler knows that that particular bowler is not so good on economy, the number of runs on an average per over, then that bowler can say, no, this economy is overrated. I really don't think that we should assign too much weight to this. So I will assign a weight of 0. It's okay. It's because we told the DMUs assign the weights that suits you best. Clearly, assigning a very large weight to this output when I know that I am not performing very well on that output, right? It doesn't suit me. So I will assign a weight of 0. Even with that, or probably because of that, the third sales office has reported a efficiency of 1. Okay. Similarly, you can go to the sales office 4, and notice I'm not going to solve this LP again, but you know how this is. This is your X14, this is your Y14, this is your Y24. Okay, and by nicely balancing the input and output weights, even the sales office 4 has reported an efficiency of 1. Even the sales office 5 will report an efficiency of 1. Sales office 5 is able to report an efficiency of 1. So far, are we matching? Go to the, yes, correct. So 3, 4 and 5, they have all reported an efficiency of 1, and therefore they are on efficiency frontier. 1 and 2, they don't seem to be on efficiency frontier. So let us check their LPs, linear programming outputs. Okay, so the first sales office has reported an efficiency of 0.68. How did it get 0.68? So let us look at this. This is X11, this is Y11, this is Y21. Okay, so this is weighted output, output multiplied by its weight, output multiplied by its weight, right? Normalizing constraint is normalizing the input. So input weight multiplied by the 2 lakhs that everybody gets, normalizing that to 1, and these constraints tell you that using the weights for DMU1, none of the DMU should report an efficiency of more than 1. So this is a weighted output for first sales office, has to be less than or equal to the denominator. Denominator is actually same for everybody. This is the weighted output for DMU2, right? Has to be less than or equal to the input. DMU3, DMU3, right, output multiplied by the output weights of DMU1, weights for DMU1 but the data from DMU3, right, and so on and so forth, right. So here we are able to say that even when first sales office had a freedom to choose any output weight and any input weight, the best efficiency that they are able to quote, the maximum efficiency they are able to quote is only 68%, and clearly this sales office is not efficient. Very similarly, sales office 2 is able to report an efficiency of only 60%, 61% approximately. 61% approximately. And clearly even the sales office 2 is not efficient for this particular data, If you change the data, probably they will become efficient. If you pick different sales offices, probably they will become efficient. We don't know. Because as we said earlier, we are only measuring the relative efficiency. So go back, and now we have validated that this graphical output was indeed true, because this actually came from DE. So 3, 4, 5 turned out to be efficient, 1 and 2 turned out to be not so efficient. Okay, hope this is understood now.